mathematicians try to study this type of systems. That is pure mathematics. Now you can try to imagine, if you wonder what sort of result can come out from such a general situation. You will be surprised to know that a lot comes out from even such a general situation. Let me state one of those results. You see, here in our case, the equations that we considered in solving this problem, there these right hand side constants were not zero, but sometimes in some situations they are zero. And if they are zero, then we have this. Such a system is called a homogeneous system of linear equations. By the way, why am I saying that these are linear equations? Because the variables appear in the first power. We don't have x1 square or x1 cube. We don't have those types of things. Okay, so that's why they are linear equations. Now, if we have 0 on the right hand side of each equation, then it's a homogeneous system. There is a result that says that if the number of variables is greater than the number of equations, then there will be at least one solution to this system where at least one xi is not equal to 0. You can see that unlike the system that we considered in solving this problem, this type of systems always have one solution. It is guaranteed to have one solution where all the variables are equal to 0. You put x1, x2, x3, etc. equal to 0 in all the equations. Because the right hand side is 0, all of them are satisfied. So this solution is always there for a homogeneous system. Sometimes that is the only solution. This is called trivial solution because it's not interesting. It is a trivial case. However, if there are more unknowns than equations, for example, here n is equal to 2, n is also equal to 2, right? Two variables s and r, two equations, this and this. So this is not this case. This case would be if we had only one equation but two variables. So in that case, there will be at least one, apart from this one, there will be at least one solution, at least one set of numbers which satisfy all of the equations simultaneously, where not all of them are 0, at least one non-zero is there. Now this sort of non-trivial, this is by no means obvious. Okay, it has to be proved. The proof, although not very difficult, but it's non-trivial. We cannot simply see why that is the case. So this sort of result comes up in pure mathematics, and the activity is like this. We deal with very general situations which look very abstract and then find some results. So that is pure mathematics. You can think of it as deciding a pair of shoes. You go to a shop and you buy a pair of shoes, but before buying, what do you see? You see whether the shoes fit you or not. So the shoes are like the parts of pure mathematics, or these results, and the shoemakers are the pure mathematicians. Some shoes may be just for display, maybe a model shoe, maybe a Cinderella shoe, or maybe some very big and grotesque shoe. that's just for show, or that is just for aesthetic, that's an art piece, it can be regarded like that. That is not fit for anyone. However, there are many shoes which fit for normal people. Now those normal people are the real world problems, and the people who are trying to find the best fit for a real world problem, I mean which shoe fits the best, they are applied mathematicians. So that is the distinction between pure and applied mathematics, and this is not a clear-cut distinction. I mean, you cannot really say what part is pure and what part is applied. In this simple situation, it's very clear, but as you go to higher parts of mathematics, the distinction becomes blurry. But that's not a problem at all. Now, what the hell is going on? This virus thing is killing everything and every possible situation, and there is no apparent solution to that. Anyway, so coming back to our situation, so what I am trying to say here is that some part of mathematics is pure and some part of it is applied. Usually the pure part is really the mathematical part, and the applied part is just trying to see what fits a real life situation. Now, some of you may be surprised to know that these numbers that appear in these equations, they need not be numbers always. They can come from some very general systems which behave like number systems. They are called fields. At one point in our discussions, we will come across fields, but it's a somewhat advanced concept in algebra.